So let's take a look at a couple different problems. Here we have a swan in a lake. It's airborne by flapping its wings and running on top of the water. If the swan must reach a speed of 6 meters per second to take off, and it accelerates from rest at an average rate of 0.350 meters per second squared, how far will it travel? Well, a couple quick notes on this one. We've talked about this before. Always identify what you know. In this case, that's our initial velocity, or original velocity. Here's our final velocity. And you can always tell by the units. In this case, meters over seconds means we're dealing with a velocity. What's this number over here? Well, this is an acceleration. And what are we looking for in this case? We're looking for how far, which is not time. What we're looking for right here is distance, or displacement, which is delta x. Which equation has all of these things in it and nothing that we're not looking for? Well, hopefully you'll recognize, oh yeah, it's this last equation here. So if we use that last equation and plug in what we know, we end up with this. And then if you solve that, and I'd like you to try it on your calculator, you should get that. If you don't get that, go ahead and try it again. You might need to put in some extra parentheses. So let's look at this next problem. A car is traveling at 10 meters per second, when it accelerates to 40 meters per second in 10 seconds. Complete the velocity graph below. So it doesn't start out at 0 this time. It starts out at 10. And it's going to get all the way up to 40 meters per second. I don't know if I drew that very well. After 10 seconds. So what do we need to do in this case? I'll try to draw that downward. This is after 10 seconds. First question is, what's the car's acceleration? Well, we can use the second equation and just plug in what we know. Ends up final velocity is 40, original velocity is 10. And the time, whoops, I got extra delta t in there. Ignore this last one here. Sorry, I left it in there even after I put it in. Is 10 seconds. And if we solve this, 40 minus 10 is 30 divided by 10. You'll get the acceleration is 3 meters per second squared. Please note you could also get that by just using the definition of acceleration, which is the change in the velocity over the change in time. In this case, how much velocity does the car gain? Well, it goes from 10 to 40, so it's gaining 30. I'm going to leave off units here in 10 seconds. Oh yeah, it's the same equation, 3 meters per second squared, and the same answer. The last question is, what's the displacement? Now, this gets a little bit more exciting. If you remember, you can find displacement by taking the area underneath the graph. But you might say, whoa, I don't even know how to do this one. Well, you can break this shape into a triangle and a rectangle. The rectangle is 10 tall and 10 wide. So this rectangle has an area of 100 meters. And this triangle is 1/2 base times height. Now be careful, the height on this one is 30 meters per second. And so if you solve this one, 30 times 10, which is the base, is 300 times 1/2 is 150 meters. So what's the total displacement? A total of 250 meters. And now it says repeat this using a mathematical equation. All right. Well, probably the easiest one, based on what we know, is this one. Our initial velocity is 10, our original velocity. Our final velocity is 40. Our time is 10. Solving it? Oh yeah, the same 250 meters. Problem number 3. A ball is thrown upward at 40 meters per second from the ground. Remember, upward we define as positive, so we're going to say it's positive velocity. If the acceleration of gravity is negative 9.81 meters per second squared, how much time will elapse before it hits the ground again? So it's being thrown up, it's going to reach a maximum, and then it's going to fall back down to the ground. Solving this one, based on what we know, probably could use this one. What's the total displacement when it comes back down the ground? I'm going to assume it lands at the same spot it started. It's actually going to be 0. Our original velocity is this number right here, positive 40. And our acceleration is negative 9.81 meters per second squared. So we plug those in and we solve for time. If you do that, you end up with this equation. And a lot of you might freak out. Yes, you could use the quadratic equation at this point, where this would be the A term, this would be the B term, and C would be equal to 0. But you can do a quick algebraic trick before we do that. Turns out you can factor out a t from both of those terms. Now, if t times that quantity is equal to 0, it means either t is equal to 0 or this whole quantity is equal to 0. If you solve that, you'll discover that you have two possible solutions. Either t is equal to 0, or if you solve this other part, t is equal to 1.15 seconds. Yes, t equals 0 is a valid solution. That's when it starts out. But we're interested in this one, the 8.15 seconds. And then the second question, what's its maximum height? You could use, now we know the time, you could solve a bunch of different ways. You could figure out, oh, the time at halfway point would be half of the 8.15 seconds. Or you can just say, all right, I can use this equation again because I don't know the time. Initial velocity is 40. Final velocity, when it reaches the very top right here, its velocity momentarily is 0 before it falls back down again. Not moving up, not moving down, briefly stop. And the acceleration of gravity, negative 9.81. And if you solve that, you'll discover it flies up a total distance of about 81.6 meters. Moving on. I wanted to spend a little time with graphical relationships, just a quick review on this one. Reminder, how do you go from position versus time to velocity versus time? The answer is to solve this, what you have to do is look at the slope of this graph at each point. The slope here starts out at 0, which means the velocity is 0 at that point. Then the slope becomes a little bit more positive. That means the velocity is a little more positive. Then the slope becomes even steeper, even more positive. That means the velocity becomes even more positive. And then over here, it's really positive, which means we have a really large positive velocity there. In general, and then how do we get acceleration? Well, the acceleration is just the slope of the velocity versus time graph. In this case, the slope at every single point is constant and positive, which means our acceleration is constant and positive. Here's the general relationship between each one of these. The slope of the position versus time, which is delta x over delta t, gives you the velocity. So the slope of these little red lines give you the velocity graph. And the slope of a velocity versus time graph, delta v over delta t, rise over run, gives you the acceleration. Likewise, and I don't know if we've talked about too much about this, the area underneath this graph will actually give you delta v. So you can work backwards and figure out the change of velocity. And the area underneath the velocity versus time, we just finished talking about that, actually gives you the displacement, how much your position has changed. And so you can actually use that to derive that one. That's an X, believe it or not. All right. So some practice with this one. Draw the velocity versus time, acceleration versus time graphs for the following accelerating objects. This one's kind of trivial, but let's go practice with it. Whoops, I accidentally drew on the screen. Let me fix that. In the first one, the initial slope of this is 0, which means the initial velocity is 0. The slope becomes more positive, which means later the velocity is positive. It becomes even more positive here, which means the velocity is even more positive here. And then it becomes even more positive here, which means our slope is even more positive here. So our velocity versus time graph for that one becomes this. How do we get acceleration versus time? Well, we've got to actually take a look at the slope. The slope of the velocity versus time graph gives us acceleration. Here, the slope is positive. Here, it's positive. It means our acceleration starts out positive and stays at this. All of these slopes are the same positive slope, even though I didn't draw very well, which means my acceleration is a constant positive. Because the slope here is constant positive, the acceleration is constant positive. Take a look at this one. And I don't know if you want to try it first before I talk about it. Slope starts out 0, which means the velocity is 0, just like before. But now the slope is now going downward. That's negative slope. And then it becomes even more negative here. and even more negative here, which means my velocity starts out 0, slope is 0 here, but then becomes more and more negative with respect to time. What's my acceleration? Well, I just have to figure out the slope of this one now. Slope's constant and negative. So constant and negative. What about this one? This one, again, you can pause the video if you want to try it first. Starts out with a large positive slope, which means the velocity has to start out large and positive. And then it becomes less and less positive, the slope, until the slope approaches 0, which means my velocity becomes less and less positive until it approaches 0. What's my acceleration in this case? Well, if you look at the slope of this one, it's a constant negative slope, which means my acceleration is constant negative. This one's a little bit more challenging. Don't panic. Here we have to work backwards. And so in this case, if the velocity is 0 here, it means the slope of this graph needs to be 0 here. And then the velocity is more positive here, which means my slope needs to get more positive here. And then the slope is even more positive here, and then even more positive here. What's the shape of this graph? It's going to be one of those exponential type graphs, although I may have missed it a little bit. It's something like that. What about the next graph? Well, this one, initially the velocity is negative, which means I need to start out here with a negative slope. And by the time I get to here, I need a 0 slope. And here I've got a less negative slope. Over here I've got a positive slope. And then even more positive slope over here. What's this shape? It's an upward facing parabola. Next graph. Velocity starts out at 0, which means my slope has to start out at 0. And then it becomes more and more negative. Actually, I'm going to move this one up here. You'll see why in a second. Starts out at 0 slope, because the velocity is 0. Then the slope is going to become a little bit more negative. Then the slope is going to have to become even more negative. And the slope is even more negative. What's the shape on this one? Something like this. Finally, the last one. Slope starts out positive, velocity is positive, which means the slope over here has to be positive. And then it becomes less positive. Then it goes to 0 over here. And then a little negative. And then very negative. And you can sort of see what I just drew. This is kind of an upside down parabola. These are much more difficult because you have to think about the slope, but you can still solve it. Last one on these before we get some practice in before the quiz. Take a look at these velocity, we need to draw the velocity versus time. These are actually pretty friendly. Slope is 0, means velocity is 0. Slope becomes more and more negative, which means my velocity becomes more and more negative. This one, slope is large and positive, which means my velocity starts out large and positive, and then it becomes less and less till it reaches the slope of 0 here. And then it becomes more and more negative slope over here. That means my velocity has become more and more negative after that point. This last one here, velocity starts out large and negative, less and less negative, until at the very end here it's almost 0. Slope large and negative, which means velocity starts out large and negative. By the end here, it approaches 0. This graph looks something like this. Find the last step, large and negative, less negative, gets to 0, becomes positive, and then even more positive. I start out with a large negative velocity. By the time I get to here, I'm 0. By the time I'm over here, I'm a large positive slope, large positive velocity. It's going to look something like that. Now some actual practice for the quiz. You've got these two objects. You've got a position versus time graph for object A and B. What's this going to look like? Well, if we graph B, its velocity is going to be the slope of this graph, and it seems to have a kind of constant slope like this. So a constant positive velocity. If I draw it, I'm going to draw it down below here. Oops, hold on a second. You'll see why in a second. It starts out ahead of the origin. Notice it's got a y-intercept there. So when I draw this one, I think I'm going to actually start it out maybe here. And it's moving fairly slowly. I'm just going to draw one every spot. Now, what about object A? Well, object A is moving definitely faster. How do I know that? Notice the slope is actually greater. I'll put a little b by these. And it starts out at the origin. Sorry, I'm not drawing enough arrow. Oh, these are really tedious to draw. What about object A? Well, object A starts out at the origin, but notice its slope is greater, which means its velocity is greater, but it's constant slope. So A should look something like this. How would it start out? It's going to start at the origin, and I'm going to make it go every 2 spots. Why? Because it has a larger velocity. So here's A, and I'll draw in little vectors on it. Dink, 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 and dink, dink, dink. And I know I could draw another one over here, but you get the idea. What about this graph? Very, very similar in a lot of ways. Let me draw B again real quick. B is almost identical to what it was before. B is just constant, starts out here. And forgive me, I'm not going to draw the arrows because it just is painful. But it's moving towards the right in this case. But what about A? A starts out, if you look at the slope on this thing, almost at 0, and then it becomes more and more positive until it actually has a steeper slope than B does. So what am I going to draw here? Something that looks like, it should be a straight line. B, or this one should start out slower, but eventually pass A. Something like this. Pass B. So starting out the origin, initially moving slower, but picking up speed the entire time. And so it's going to go much, much faster. And again, I could draw arrows on that, but you get the idea. Take a look at these graph ones real quick. This is actually fairly similar. Question is, how does the motion of A differ from that of B? I'm going to skip the motion maps on this one. How does A differ? A is actually moving at a constant positive velocity, whereas B is gaining velocity the entire time. Why? How do I know that? Its slope is increasing the entire time. And now, just a couple of quick questions on this one. How would you compare these? So at 5 seconds, they cross. What does that mean? Well, since this is a position versus time graph, at that instant, their displacement is actually equal. The reason we know that, they have exactly the same position. Average velocity, that's a little trickier. Average velocity just means, hey, what was the velocity from when it started here at 0 all the way out to here? Well, think about it. Velocity is defined as how far you travel divided by the time it takes. By the time they get to 5 seconds, they've both traveled identical distances in the same amount of time. So their average velocities are exactly the same. The total displacement, 5 seconds, is the same, and the time it took them to get there is the same. Now, the instantaneous velocity, that's where it gets a little bit more exciting. If you look at it, A's velocity at that instant is the slope of this line, whereas B is the slope of this line. So in this case, B's velocity is greater than A. How do we know that? Because the slope is greater. And now, take a look at this one. Now be careful, this is a velocity versus time graph. What does this mean? It means A is going at a constant 4 meters per second the entire time. And so if you graph it down here, it would be equally spaced as you're drawing it. And B, what's happened to B? It starts out at 8 meters per second, and it slows down to 0 after 5 seconds. So B's velocity decreases. Now be careful, don't get these confused. The previous graph was position versus time. This is the velocity versus time graph. What's happening here? It's starting out very fast. It's only moving, almost moving twice as fast. But then it's going to be losing speed, losing speed, losing speed, until now it's going slower than A, until eventually it stops. Again, I should draw arrows for this, but you get the idea. Comparison? Now here's where it gets a little bit exciting. Displacement at 5 seconds. Who went further? Well, if you look at this, A traveled, remember displacement's the area underneath the graph. A traveled this far in the 10 seconds. It would be the entire area underneath its curve. And forgive me trying to draw all these. So if it traveled 4 meters per second for 5 seconds, what's its displacement? The answer is, this is 20 meters. How far did B go? Well, if you look at it for the entire time, it would be, and I'm going to just scribble on this one, the area of this triangle. The area underneath the velocity for B. What's that? Well, remember, triangle's 1/2 base times height. Ironically, it would give you 20 meters as well. So who has a greater displacement at 5 seconds? The answer is, believe it or not, they're equal to each other. Now, what about their average velocity? Well, for A, it's just 4 meters per second. For B, it started out at 8, ended up at 0. Its average velocity then, 8 plus 0 divided by 2, is still 4. They actually have the same average velocity over that entire interval. They actually went the same distance in 5 seconds. Who has a greater instantaneous velocity? Well, in this case, A wins. Why? A's still going 4 meters per second, whereas B at this instant is actually going 0. And you can see that from the graph. All right, you should be pretty much prepared for the quiz. Good luck. You can work with your neighboring partner. Have fun with this. Take your time with it. When you're finished, you have some graphical review, similar to what we just did for homework. Good luck.